Hi there, Justin Kreft here, presenting my project for 690 entitled Stars and Location. It is based on mining Yelp data. The problem definition for this particular project was to assess if the old adage location, location, location is actually true for restaurants. Put another way, is there a relationship between clusters of restaurants that are in close proximity with each other geographically and their star ratings? In other words, if I go to a particular location, and will I tend to find restaurants that are higher rated as fours and fives if other restaurants in that area are also already fours and fives? So that was the basic attempt. There were 4 stages to this project: pre-processing and data selection, and I'll go into each of these. Cluster analysis, where I actually took the latitude and longitude and tried to create clusters that I would use later. I evaluated these clusters against the neighborhood clusters tagged, or the neighborhood basically labels tagged in Yelp. And then in stage 3, I used the cluster labels that I had generated to as evidence to see if I could predict star rating. And then in stage 4, I evaluated the different models that I had generated across 10 folds, 100 folds, and then the hold one out method, which took a really long time. And then also calculated significance of the differences with a Fisher's randomization test, which I'll go into. So in pre-processing, I needed to limit, first of all, to restaurants only, no doctor's offices, etc. And then I also only wanted to do one city because I felt like creating clusters across latitude and longitude would be very difficult if between 2 different cities, especially if they spanned a very far distance away from each other. So I wanted to focus in on just one city. I collected features from many different data sets, business neighborhoods, business categories, which I split and created out of Python, business tips, that's the sum total number of tips that the business had, how many check-ins they had, how many, what kind of features they had, for instance, what times were they open, were they good for kids, they serve alcohol, etc. And then also the features of reviews, like how many votes cool do they get, and how many votes useful, and etc. And how many reviews did they get, and what were the average number of stars, etc. I joined all of those together and then output 2 files, one to go to stage 3, where I would join it with the results of stage 2, and the other one for stage 2, which was just comprised of latitude and longitude and the business ID. So 1,361 businesses went to the next stage. So cluster analysis, I actually evaluated 3 different cluster algorithms and compared them to neighborhood labels that Yelp had already collected. I could do that 2 ways. One, visually through OpenStreetMap views, which we will go through in a moment, and then objectively, so subjectively here, but objectively through an entropy score, which compared the 2 data sets and identified whether my cluster labels increased or decreased entropy overall. Here we have a picture of the neighborhood labels as listed in Yelp naturally, and we see some pretty nice groupings as you would expect in sort of home folksonomy taxonomies created by users. However, there remain a lot of businesses that are for unclassified, they're unlabeled. All the red is currently unlabeled as not belonging to a neighborhood. And that's problematic because if we were just going to run the calculations just based on neighborhood labels, we would be eliminating a great number of businesses from our data set and only concentrating on these sections. Plus, we aren't able to actually subsect any of these large, dense clumps at all. So I felt like just using neighborhood labels wouldn't be useful. So the first algorithm that I did, very simple, k-means. It's very easy to do, and the result that I got in the OpenStreetMap was very similar to the neighborhood. This is a k-means of 50, and you'll see that they're very close in terms of the shapes that they produce. And the benefit of k-means was that I actually was able to group these outside neighborhood or outside suburb restaurants together in maybe some meaningful way, but in a way. The problem that I had is I still wanted to get subsections here in these really dense clumps. And the more number of clusters that I told k-means to create, instead of creating them here in the dense clusters, it tended, naturally because of the way it's calculated, it tended to create clusters out here where it's not as dense and it was easier to separate them. And that's a real problem because eventually I would just end up with a bunch of noise, which is exactly what I was facing in the previous map for the Yelp labels. So I needed some other way of doing that, and I decided, well, the natural next step would be some sort of density-based clustering algorithm like dbScan. And my thought process was that, hey, maybe I will be able to create some interesting shapes and actually get subsections of the dense particles, the dense groupings, instead of anything weird. So here is a picture of dbScan, and I did get some really great nice clumps, and a little bit different than the neighborhoods or the k-means. The only problem is I walked right back into the noise problem, because dbScan, if it can't classify it, it classifies it as noise, and noise is all over the place. So this didn't help me really create labels for all data, and I quickly had to abandon dbScan entirely. My last-ditch effort and the hero was actually hierarchical clustering, which is a bottom-up clustering algorithm that uses a distance. In this case, I chose Manhattan, and a particular assigner, a way of calculating that distance, or calculating how you're including something into a cluster based on that distance. And I chose complete because it gave the nicest looking clusters. And if we look in it, we will see that it's actually really nice. We did get some breakup in the dense stuff, although not in central Pittsburgh, but in some of the outlying areas we got some breaks. This used to be all one big huge section, and now it's separated in one or two or three. And we still managed to group all the outlying areas into separate clusters without pumping them into just groups of one or two. So I succeeded in generating about 50 clusters of data for including all of the different businesses, and that was a good success. So we've just superficially analyzed the three different, but I wanted to compare something on objective measures as well. So I used the entropy score built into KNIME to do that. And basically, the entropy score again just compares the labels as in the clusters that you generated against the labels that were in the in the Yelp neighborhood labels. And when you do that, you get whether or not we increased or decreased entropy, or rather, what is the entropy of the clusters as compared to the labels of the reference group, and whether it's a good quality or not. So it's a very simple way of evaluating a cluster if you have a reference list available to you. And here we see 3.4 entropy for the k-means quality of a score. Okay, here is dbScan. It got a little worse, and then we did the hierarchical clustering. It got a little better. I did find that if I increased the number of clusters for the hierarchical from 50 to 100 or even 150, the entropy went way down and the quality went way up, which was awesome. However, it created problems for me downstream in that I got a lot of one-offs, and the result was I couldn't do any classification classification. So I stuck with 50. So now to classification. I took the labels that I generated and I merged them back with the features that I had pre-processed, joined them together, and then I sent it out to Weka to be for feature selection, and then pumped those back out and messed around with them in the actual classification. But let's just go into the Weka tool real quick. I did find that the best labels, the best features for predicting certain classes, if I was trying to predict cluster labels, the clusters that I created, actually neighborhoods and some cuisines were the best. That's not surprising at all. However, interestingly, if I wanted to predict stars, which is the whole point of this project, which is predicting stars, cluster number, the clusters that I generated, were the highest feature in terms of predicting. So I thought that put me on a really great track. Attributes, price range, and review count were also highly correlated to the star class. Average stars were most influenced by some votes cool, and check-in count, how many times people checked in. That was also highly correlated with cluster number, and also the number of stars that they were given, and the review count of the business, the number of reviews that the business had. So with that information, I narrowed down the features that I was willing to analyze into my models, and I proposed 3 models that used the clustering labels that I had created. I compared them against one model that only used the labels that for the neighborhoods in Yelp, okay, just as a baseline, but that actually ended up not being very useful. And then finally, I used all the same features, but I eliminated the cluster labels that I had generated. So now I'm using just the data set without the clustering information. I created 3 models based on that, very similar to these 3 here, to compare basically whether or not my cluster labels were adding something or subtracting, etc. I did a decision tree learner based on all of the information, so all of the features, and then also the cluster labels. I did a decision tree learner on just the cluster tree labels, or the cluster labels that I had generated only, as a way of seeing if I would do better or not if I didn't use any of the other data. And then I did a logistic regression using only the cluster labels, or the cluster labels. And then I did similar things down here. This is the X partitioner. It loops through this model. This is where I chose whether or not I was going to do 10, 100, or hold one out times. I did some of this in RapidMiner as well and sent it back in. So I've used other tools as well. So once I generated these models for the 10, 100, and 1 holdout folds, I was able to score the results, and then I was able to see the accuracies of each of the models. So here we have each of the models that I created and their accuracies and kappas across the different fold measurements that I had done. And we basically see no model did better than 66%, which was Model 5. Model 5 was no cluster labels, but all data. And of the group, the first 3 that used cluster information, the best percentage, the accuracy percentage I got was 0.62. Okay, all right. So it was interesting to look at this, but I didn't know if any of this information was meaningful. Like, I couldn't say definitively with what I had whether Model 5 was better than Model 1, or if Model 1 or 2 here, let's say Model 3 was better than Model 1. Okay, so I couldn't decide, I couldn't find out. Great, we've got an accuracy, but that doesn't necessarily mean that that's meaningful. So I took all of the error rates for each of the different folds that I had calculated, and I dumped those into a data set, joined them all together, and actually used Fisher's randomization, which I learned about in another class, and I wrote a quick Python script to do it. And it basically takes two sets and it calculates a test statistic, and then it does Fisher's randomization, which you can look it up, but it's a really good way of coming up with a p-value to see if something is statistically significant when comparing two different models to each other based on a similar test statistic. And when I compared each of the models together, these are the p-values for each of those, and basically the only one that was consistently significant across all of the different fold structures was model 5 always performed better than 1, and that was statistically significant. And I'll go into that in a second. 5 also did better than model 2, and that was usually statistically significant. And then lastly, model 7 did better than model 3, and that was statistically significant. So that's bad news bear for me, because models 1, 2, and 3, if you recall, were the ones that I built based on the cluster labels. Models 5, 6, and 7 were the ones that I didn't use the cluster labels, and actually 7 was the most interesting one. I used all the data, and then I also used latitude and longitude. And it's kind of sad because a statistically significant result showed that just using latitude and longitude was better than the clusters that I had generated. Okay, fine. So what are our findings? There's a small difference between the models compared. Only a few were statistically significant as compared to each other. And the most successful models at predicting stars greater than or equal to 4 with statistically significant p-values in comparison to the others models were those that, 1, didn't use cluster labels at all, model 5, or simply used latitude and longitude in place of the clustering that I performed. So my clustering didn't add anything. Okay. So while my conclusion is while there is a correlation between some clusters and star ratings, and that's obvious if you look at scattergrams and everything. I mean, there's clearly a high distribution of higher ranked 4 and 5 star restaurants in some areas, on some clusters, like downtown, like a couple of high economic areas. However, location cannot be used to predict a star value across all clusters. So, in other words, so location is not necessarily the particular location or the proximity to another high star place is not necessarily true across all different clusters, probably just a few types of clusters. So there's something else at play here, obviously. So although my naive, attempt at answering this question was not successful, I think it was very useful as a way to learn this material, and I did learn a great deal from it, and enjoyed doing it. Wish it would have resulted in a success, but negative results are also interesting in their own right as well. So thank you very much.